In the last lecture, we have seen how to find out eigenvalue, eigenvectors, how to find out the characteristic equation. We have also seen the Calle-Hamilton theorem and then how to solve the problem based on Calle-Hamilton theorem. We have also seen that how we are able to miniaturize the given system using Calle-Hamilton theorem. Now we'll see the concept of similarity in this lecture. Okay, so first we need to define what is the similarity of matrices. So to have the similar matrices, we need to understand the property. Yeah. I hope
Sir,
you
can
are
you,
able to see the Jamboard.
sir, can you share the link of Jamboard?
Okay. Yeah. I have again shared the link of Jamboard. Okay. So I hope you are able to see the Jamboard now. Yes.
Yes, sir.
Yes, sir.
Okay. So we need to understand similarity of matrices. Okay. So when we say the two matrices are similar, okay, so there is a difference between equality and similarity. So we can say A is equal to B if the dimension of A and dimension of B is same and every corresponding element is going to be same, then we say A is equal to B. But similarity is something different than the equality. Okay, and that's why we need to understand what is the similarity. So what we have to understand is let A and B being two non-zero matrices of same order, and if there exists a non-singular matrix P of same order such that B is equal to P inverse AP, then B is said to be similar to matrix A. Also, we have, so if we can write B is equal to P inverse AP, then I can write this A as, see, this P will be here, P will be here, and this
Excuse
is
me,
P
sir. Please
inverse.
send the Jamboard link again.
Yeah,
The Jamboard link.
okay. You can have it now there. Okay. So you can see if we can write B is equal to P inverse AP, P is going to be non-singular, so P inverse exists, and hence P, since P inverse exists, the inverse of P is again P. So we can write A is equal to P B P inverse. So B is similar to A, . is denoted as B tilde, this is all tilde, similar to A. Also, we have A is similar to B. So when I say B is similar to A, obviously we can say A is similar to B. So this similarity is a reflexive relation, okay, or symmetric relation you can say. Moreover, it is a equivalence relation, and so this symbol is also used for equivalence relation. Okay, so we got the matrix A and B, which are of the same size, same order, then they are going to be similar if there exists a matrix P which is non-singular. Non-singular is necessary because we want its inverse. So the non-singular matrix P such that if this happens, we can say these two matrices are similar to each other. So is there any doubt in the similarity of two matrices or the definition of similarity? Durvesh, you got the definition of similarity? Arpita? Arpita, are you there?
Yes, sir.
Yeah, you got the definition of similarity?
Yes, sir.
Okay, that's good. What about Rajat? You understood the definition of similarity, Rajat?
Yes, I understood.
Okay, that's good. So I hope every one of you have understood the definition
Yes,
of
sir.
similarity. Now, one important thing we know. Okay, so we know about the diagonal matrix. So can you, any one of you, tell me what is a diagonal matrix? Can any one of you tell
The
me what is
diagonal elements of the matrix.
Hmm? Yes, Aditya?
A matrix in which only there are like diagonal elements, all other elements are zero.
Okay. Anything about these diagonal elements? Any relation for this or any restrictions for this diagonal elements?
Diagonal elements are same.
It should be
Diagonal
1.
elements are same.
Cannot be 0.
Cannot be zero. That's good. So when we say a matrix is diagonal, okay, a matrix precisely square matrix. A square matrix is said to be diagonal matrix if its off diagonal elements are zero and at least one of the diagonal element is non-zero. Then we say the matrix is going to be diagonal matrix. Okay. Now, if the matrix is similar to diagonal matrix, okay, so what we can say is we have another concept, okay, called diagonalizable matrix. Okay, so what we have, diagonalizable matrix. Now, a square matrix A is said to be diagonalizable if it is similar if it is similar to a diagonal matrix. D. That is, the matrix A is said to be diagonalizable if it is similar to a diagonal matrix D. Hence, there exists a non-singular matrix M such that D is equal to M inverse AM. D is equal to what? M inverse AM. And hence we can write this also A is equal to MD M inverse. Okay, so where D is called diagonal form of matrix A and M is called model matrix. It is also called as diagonalizing matrix. It transforms the matrix A into diagonal form. So it is also called as transforming matrix. So all these names are same. M for model matrix, it diagonalizes, so it is diagonalizing matrix. It transforms, so transforming matrix. Okay. Moreover, D is matrix of eigenvalues of A, and M is matrix of corresponding eigenvectors. Yeah. So while writing D and M, we have to be careful. So in which order we are going to write the eigenvalues? In the same order you have to write eigenvectors. So for example, let A be a 3 by 3 matrix. Hence, we have E is equal to, so it is lambda 1 0 0 0 lambda 2 0 0 0 lambda 3, and M is equal to, so column wise x1, x2 and x3. So first column is a first eigenvector, second column is a second eigenvector, and third column is a third eigenvector, where A is diagonalizable. So A has to be diagonalizable. So if this matrix A is going to be diagonalizable, then we can express this A as, that is what we can write, D is equal to M inverse AM, and A is equal to MD M inverse. Okay, so where D is the diagonal matrix of eigenvalues and M is a matrix of eigenvectors corresponding. So this is very important. Okay, we have first eigenvalue and then first eigenvector. We have second eigenvalue and then second eigenvector. We have third eigenvalue, then third eigenvector. We cannot exchange the places of this. Okay, so we cannot have the third vector corresponding to the second eigenvalue. No. So we have to understand the order, in which order the eigenvalues will appear. In the same order, eigenvector has to be appear. Okay, so all the eigenvectors will follow the same order of the eigenvalues. Okay, so if this relation is satisfied, then we say the matrix is going to be diagonalizable. So is there any doubt in these concepts? Is there any doubt in similarity or
No,
in diagonalizable
No, sir.
matrix?
No, sir.
No, all of you got this one? Have you got these concepts?
Yes, sir.
Yes, sir.
Okay, that's great. Okay, so once you are able to understand this concept, let us go for the another one. Okay, so now it becomes difficult to find out the matrix. Okay, and hence what we do is the easiest way is finding the eigenvalue eigenvector. But still, we cannot guarantee the inverse of M exists. Okay, so if these are repeated, then we are in trouble. Okay, so that's why we have to be careful. So when we can guarantee that M inverse exists. Okay, because we cannot say that there exists inverse for every matrix. Okay, and hence, if we want to give the guarantee that M inverse exists, then some more terms we have to consider. So we have to consider algebraic multiplicity of eigenvalue. Okay, so we need to understand what is the algebraic multiplicity of the eigenvalue. Okay, so easily we are able to define this, but then again we have to revisit the characteristic equation. Okay, so what we can say is the number of times eigenvalue is repeated in characteristic equation is called algebraic multiplicity. Of eigenvalue. Okay, and is denoted by am of lambda. Okay, algebraic multiplicity of eigenvalue. So we have to see that how many times it is repeated in the characteristic equation. If it is repeated one time, it may be repeated two times, it may be repeated three times, and like that. So, number of times it is repeated is going to be algebraic multiplicity. Now, we need to understand geometric multiplicity. So, we can see the algebraic multiplicity we are able to calculate from the characteristic equation. Now where to calculate the geometric multiplicity? So the geometric multiplicity is nothing but the number of vectors associated with the eigen value. Okay. So the number of non-zero linearly independent vector corresponding to the eigenvalue is called geometric multiplicity. This is going to be geometric multiplicity and is denoted by geometric multiplicity of lambda. Okay, so here we need to understand two things. Okay, one about the algebraic multiplicity. So algebraic multiplicity we are able to get from the characteristic equation, and the geometric multiplicity we are able to get from how many eigenvectors are associated with the given eigenvalue. So once you have the geometric multiplicity and algebraic multiplicity, then you can think of the diagonal, whether the matrix is diagonalizable or not. Okay, so now it's time to redefine diagonalizable matrix. So one way is finding the matrices M and D, but how to find that matrices M and D? So we must calculate the eigenvalues and eigenvector, and easily you are able to get the matrices M and D. And so you can say, yes, that this matrix is going to be diagonalizable or not. Okay. So the square matrix A is said to be diagonalizable matrix if algebraic multiplicity of lambda I is same as the geometric multiplicity of lambda I for all I. That is, algebraic multiplicity that is algebraic multiplicity and geometric multiplicity is same or equal for all eigenvalues. This should be true for all eigenvalues. Then only we can say values. Then the matrix is diagonalizable. Okay, then we say the matrix is diagonalizable. Okay. Is there any doubt in this definition of diagonalizable? Because we have redefined now. The first one is, if you can find out the matrix M such that D is equal to M inverse AM, then we can say yes, A is going to be the diagonalizable matrix. But then, in general, it is not possible to find M and M inverse. So what we do it is, we calculated the eigenvalues and eigenvectors, and then we are trying to find whether it is diagonalizable or not. And this condition will be satisfied if the algebraic multiplicity of every eigenvalue is same as the geometric multiplicity of every eigenvalue. So, considering the algebraic multiplicity and the geometric multiplicity of each of the eigenvalue, we can say yes, the given matrix is diagonalizable, or we can decide the given matrix is not diagonalizable. Okay, so is there any doubt?
No, sir.
No, sir.
Okay, okay. So that's great. You got this concept. Okay. Now we'll try to solve the problem based on this. So let us try to solve the problem. So we have the question here. I hope all of you are able to see this.
Yes, sir. Visible.
Okay. So we have the question: find the eigenvalues and eigenvectors of this matrix, and then we have to also find algebraic and geometric multiplicity of the eigenvalues. Okay, so basically what we have to do is, we just have to find out the eigenvalues and eigenvectors, and we can decide whether this matrix is diagonalizable or not. So let's go with the solution. Okay, what will be having? Let A is equal to, so it is 2 0 0 1 2 1 minus 1 0 1. Okay, so this is the matrix B, the given matrix. Then we have, so what is the first thing that we require is determinant. So if I want to find out the determinant for this, what I can have? 2 0 0 1 1 2 1, and we have minus 1. Okay, so let's have this determinant here. 2 0 0 1 2 1, and then we have minus 1 0 1. Okay, be careful, we are finding determinant. So what is that? 4.
4. Yes, sir.
Yeah, that's good. Then consider the characteristic equation of A. That is, what do you have? Determinant of A minus lambda is equal to 0. So 2 minus lambda 0 0 1, 2 minus lambda 1, minus 1 0 1 minus lambda. Okay, and this is equal to 0. If you remember the shortcut, what is that? Lambda cube. Okay. Minus S1 lambda square plus S2 lambda minus determinant of A equal to 0. Okay. And hence, using this, we'll try to find out what is the polynomial. And then we'll go for factorization. So, what we got here? Lambda cube minus sum of the diagonal element. So it is 5 lambda square plus lambda and sum of the diagonal minus of diagonal element. So for this, what will be having 2 and this term. So it is going to be 2 plus. For this 2, we have this 2 and this is going to be 0. Okay, for this 1, we will be having this 4 and minus 1. Now determinant, so you have already calculated and that is going to be 4. Now simplify this, lambda cube minus 5 lambda square, what will be having here, plus 8 lambda minus 4 is equal to 0. So can you factorize this polynomial and give me the values, the factors first and then the values?
Sir, 1, 2, 2.
1, 2, 2. Okay. So you can easily check the product is going to be 4 and the sum is going to be 5. Okay. So you got lambda minus 1 into lambda minus 2 bracket square and that is equal to 0. So you can say the eigenvalues are, what will be having, this minus will become plus. So it is 1, 2, 2. Okay, so how many times 1 is repeated?
Only one.
Only one time. So we can say, hence, we have algebraic multiplicity of 1 is equal to 1 and algebraic multiplicity of 2. How many times 2 is repeated?
2 times.
2 times. So the algebraic multiplicity of 2 is going to be 2. Okay. Now we have to find the geometric multiplicity. So what we can do is, so now for lambda is equal to 1. Okay, so we have to find out a minus lambda I into x is equal to 0. So here, if we consider lambda is equal to 1, then what is the first entry we have? What is the first entry for the matrix? Is going to be 2, no?
2 minus lambda.
So lambda is going to be 1. So how much will be remaining?
1.
1. Then this is going to be 0. What about this?
1, 1, 1.
What about this?
Minus 1, 0, 0.
Minus 1, 0, 0. Okay. So here we got x1, x2, x3. And this is what we have, 0, 0, 0. Now, can you tell me whether the Cramer's rule is applicable or not?
It's applicable. We have
Yes, sir. It's applicable.
How many distinct equations we have?
2.
2.
Pakka?
हाँ sir, पक्का.
No, sir, 3 है.
How many distinct equations we have? 2 or 3?
3, 3.
3, 3.
3, sir.
Are you sure?
Yes.
Yes sir.
1, sir.
2 equations sir.
2 है, sir, 2 है.
Okay, I'll write the equation, then you can see easily. Okay, so x1 plus 0x2 plus 0x3 is equal to 0. x1 plus x2 plus x3 is equal to 0. Minus x1 plus 0x2 plus 0x3 is equal to 0. I can write this equation as minus x1 minus 0x2 minus 0x3 is equal to 0. Now you can tell me how many equations we have.
3.
2, sir.
Are you sure that we have 3 equations?
Two equations. Sir.
Two equations.
This is
Minus
just a
1,
negative
1.
of the first one, no?
Yes, sir.
So we have only 2 equations. Okay, this equation is negative of the first, so we have only 2 equations. So if we have 2 equations, is the Cramer's rule applicable?
Yes.
Which 2 rows you want to consider?
First and second.
First and second. So we can say, what we can say is, by Cramer's rule, we have. So what we'll be having? See here, x1 upon, we'll be having 0, 0, 1, 1 equal to minus x2 upon, what will be having? 1, 1, 0, 1. And this is x3 upon 1, 1, 0, 1. Okay, so what we can say is x1 upon, this is going to be 0 because these terms are going to be 0, equal to x2 upon, this term is going to be minus 1, and this is x3, what we'll be having is going to be 1. Okay, so we can have, hence x1, the first vector is 0, minus 1, 1. Is that okay? Are you getting this?
Yes, sir.
Yes.
Yes.
So the first vector is 0, minus 1, 1. Now tell me how many vectors you are getting here corresponding to lambda is equal to 1.
3.
So is the eigenvector corresponding to eigenvalue lambda is equal to 1. So how many vectors you have? How many vectors you have corresponding to lambda is equal to 1?
2.
There are 2 vectors. Is there x1, x2 corresponding to lambda equal to 1?
One vector.
There is only one vector. x1 is corresponding to lambda is equal to 1. And hence we can say the geometric multiplicity of lambda is equal to 1 is 1. Okay, because there is only one eigenvector corresponding to lambda is equal to 1. So now we have, for lambda is equal to 2. What we'll do is consider determinant of a minus lambda I into x is equal to 0. Okay, so we can have now lambda is equal to 2. So is it going to be 0, 0, 0? See here, this will be 0, 0, 0, no? Now we'll consider the second, so it will be 1, 0, 1. Okay, so you got here, this is going to be 1, 0, 1. And now what will happen to this last? So it is minus 1, 0. So it is minus 1. Okay, so here we have, this is minus 1, 0. and we have 1 minus 2. So it will be minus 1 again. Is that okay? Because you are having this 1 minus 2, no? So is it okay?
Yes, sir.
Yeah. Okay, and here we have x1, x2, x3. And this is equal to all zeros on this side. So now tell me how many distinct equations we have?
Only one.
Only one. Okay. So is the Cramer's rule applicable?
No, sir.
No.
No. Okay. So that means we have only one equations. So we have only one equation. So what is the equation we have? X1 plus x3 is equal to 0. Okay, because we have this term equal to 0. So x1 plus x3 is equal to 0, and hence I can write x3 is equal to minus x1. Is that okay? Are you reading this one?
Yes, sir.
Yes. Okay, and hence what we get here now, the next eigenvector x2 is equal to, so we can see whatever I'll put x1, I'll be having negative of that as x3. So if I put x1 is equal to 0, then this x3 will be minus 1. Okay. Now, apart from this, you can see that any value of x2, any non-zero value of x2 will satisfy this. Is that okay? Are you getting this system? If you look at this system, any non-zero value of x2 will satisfy these equations. Is that true? Adesh, if I put any value of x2, will this satisfy this system of equations? Because we have here the coefficient of x2 is equal to 0, no? So whatever value of x2 we use, it is going to satisfy this equation. Because
Yes, sir.
the coefficient of x2 is 0 for all the equations. Okay, and hence we can say, and x3 is the vector 0, 1, 0. Okay, so if we put any value of x2, this equation will be satisfied. So are the eigenvalues, eigenvectors now, vectors of eigenvalue lambda is equal to 2. So we have geometric multiplicity of lambda is equal to 2 is, what is the geometric multiplicity? How many vectors we have for this lambda is equal to 2?
0.
0 vectors we have.
No, sir.
How many vectors we have?
Two vectors.
Corresponding
Two vectors.
2 vectors. Okay, so the geometric multiplicity of lambda is equal to 2. We have calculated and it is going to be 2. Now see, the geometric multiplicity of lambda is equal to 2 is 2. The geometric multiplicity of lambda is equal to 1 is 1. The algebraic multiplicity we have considered. So algebraic multiplicity of 1 is 1 and the algebraic multiplicity of 2 is 2. So can we say that this all eigenvalues has the same algebraic and geometric multiplicity? Hence we have algebraic multiplicity of lambda I is same as geometric multiplicity of lambda I. Is this statement true? Can we make this statement?
Yes, sir.
Yes, sir.
Yes. Okay. And if this is true statement, then we can say the given matrix is diagonalizable, and hence the matrix A is diagonalizable. So this matrix A is going to be diagonalizable. Now, see the question. So what it says, find the eigenvalues, eigenvectors, also find algebraic and geometric multiplicity. So we got a geometric and algebraic multiplicity, and we proved that it is going to be the diagonalizable matrix. Okay, so if it is a diagonalizable matrix, what is the diagonal form? And then what is the model matrix? So we have the diagonal form of A as, so D is a matrix of eigen values. So it is going to be 1, 2, 1, 0, 0, 0, 2, 0, 0, 0, 2. And the model matrix, or this is also called as transforming matrix, M is, so M is equal to the eigenvector corresponding to 1. So what is eigenvector corresponding to 1? 0, minus 1, 1. So we got here 0, minus 1, 1. Then these are repeated, so you can choose any of these values. So it is going to be 1, 0, minus 1, 1, 0, minus 1, and 0, 1, 0. So this column you can write here also, and this column you can write here also, because the eigenvalues are going to be same. But we need to understand the correspondence. So for the first, we must have the first. For the second, we must have the second. And for the third, we must have the third. So for first eigenvalue, we'll have the first eigenvector here. For the second eigenvalue, we'll have the second eigenvector here. For the third eigenvalue, we'll have the third eigenvector here. Okay, so this way, when you will write this in order, definitely this M is going to be invertible matrix. If you write the matrix M like this, okay, so I am changing the order now. 0, 1, 0, 1, 0, minus 1, and then this is 0, minus 1, 0, minus 1, 1. Okay, so for this matrix is wrong. Okay, though the eigenvalues and eigenvectors are going to be same. Okay, but this is not in order, and that's why this cannot be considered. So we have to be very careful while writing the eigenvalues and eigenvectors in matrix M and D. Okay, so whatever the order we use in D, the same order should be followed in matrix M. So is there any doubt in this question?
No, sir.
This
No, sir.
concept? Okay, that's good. So all of you are able to get the definition of similarity, the concept of similarity, and diagonalizable matrix.
Yes, sir.
Yes, sir.
Yes, sir.
Any doubt?
No, sir.
No, sir.
Okay, that's good. So you don't have any doubt. It's very good.